Hi, everyone. I'm Priyom. I'm currently a postdoc at Duke, but during my time in James's lab, I played a lot around with the focal point plasticity plugin, and I'm going to tell you a few exercises that we're going to use the plugin in more. So I'm sure you're pretty much pumped and still have a lot of energy to go on and do more exercises. But well, the good news is Julio has already covered a lot of the features that we'll be exploring today. And the simulations for all of the modules have been uploaded. The last two modules are a little more Python heavy. So if you don't feel like following and writing the code, feel free to download the modules and we will go over the output together. All right, so just to give you sort of like what we'd be covering in this module. So we're going to quickly recap building an epithelium. Julio has already shown you how to basically use compartmentalized cells to represent different parts of an epithelial cell body. We'll be using that basic code to sort of connect our compartments with links using the focal plasticity plugin. And what we're going to do is sort of generate or basically increase certain parameters of this plugin to increase the forces in particular regions of the tissue and create tissue folding. And we're going to sort of like walk through a few of these exercises. I'm going to keep a lookout on the chat, but if I take a moment, please, I'm sorry about that, but I'll keep a lookout on the chat. Okay, so sort of like to give you a motivation of why we're doing this. So during development, what we have seen are these large-scale morphogenetic movements that are coordinated by groups of cells changing elongation and other cell behaviors. And the resultant of these changes at the cellular level are tissue folding events or invagination, as we can see from examples in neural tube closure, gastrulation, in which the exposed apical surface of the body actually folds inward and then begins the germ band specification in the embryos. So all of these are sort of like important events. And at the sort of like core of this lie the advantage that cells have in polarizing their body, because cells can deposit or basically have concentration of adherents or tight junctions along the cell body, which are very useful at implementing forces that can change the shape of the whole tissue. And coupled with the establishment of these junctional complexes are the intracellular machinery, which is combined in a whole network-like fashion that's able to transmit these forces on larger scales. And so one of the processes that we're going to sort of like mimic is the process of apical constriction, in which we are going to construct a tissue layer comprising of a basal and an apical side. And we're going to add links on the apical side and sort of try to fold or give excessive force on certain tissue regions and sort of like fold the tissue inward. And that's sort of like our overall goal for this module. And the other thing I'm just going to like say is, so a lot of the things that you have already seen how to build an epithelial layer at this point. So we have a couple of options here before I go any further. You can either download the code from module 6.1 from today morning that shows you how to build a compartmentalized cell epithelial layer. And on that, what you can do is additionally add the focal point plasticity plugin so that you have connections only between the apical side of the cell body. And we can after you have done those steps, we can talk about how to basically induce folds. So what you can do is you can mute me at this point and meet me over there, and we can go over the folding part together if you want to explore it on your own. But what I'm going to be doing is sort of walking through what you have already seen till this point in a little bit more detail. If you want, we can build a simulation together again, if there are any other points that you'd like to talk about, and then we will induce the tissue folding process. Okay, I'm going to quickly look at the chat. Okay, perfect. So let's say, so this is basically the plan for the module. And if these are some of the additional steps that you'd also like to implement on your own, feel free to do so. So what we're going to do is we're going to work with the epithelial cell layer that you already saw. We're going to have 4 specific cell types. We're going to call them apical, lateral, basal, and ECM. We're going to add the focal point plasticity plugin. We're going to modify some properties of the uniform initializer that Compusel automatically generates for us. What we're going to do is we're going to build each of these cells with 7 pixels. And we're going to stack them on top of each other, starting with the ECM at the bottom, the basal layer next, the lateral layer next, and then the apical layer. We're going to then move on to the focal point plasticity plugin, and we're going to make sure that, one, we have connections only between the apical and apical site. And we're going to basically set all the parameters in the XML file to 0. And the goal for this is so that we can actually modify the focal plasticity plugins from the Python steppables file that Julia showed you a while ago. And we'll be mostly working with the steppables file to modify our plasticity plugin here. Another thing which Julia already showed you is that we have to also make sure that in the compartmentalized cell that's representative of a whole cell body, we have to make sure that the contact energies the internal contact energies are cohesive, so that we have a whole, like the 3 compartments wanting to stay together. But they should also the external contact energy should be that the compartments of the same kind are laid side by side. So we have to arrange both the internal and the external contact energies in this case. And finally, once we have done this, we also want to make sure that the cells know that they're part of the same cluster. And we have to reassign cluster IDs in this process in the steppables file again. And finally, what we'll do is, using the steppables file, again, we're going to find neighbors along the apical site, and we're going to join them using the focal point plasticity link. And we're going to modify all our parameters there. So these are the couple of steps. This does not include the folding part yet. You have seen this already, so feel free to play with it on your own. But I'm going to walk us through these steps now. I'm going to quickly see if you have any more chat questions. Okay, all right. So the first step that you already have seen on how to generate sort of basic focal point plasticity plugin. But if you want a refresher, feel free to go to your to edit file, and feel free to change up your dimensions and along the X and the Y axes. Here I've set it. So what we are going to do is, after we have set up the parameters of the simulation, we are going to add 4 cell types. Like I said, we are going to add an apical, lateral, basal, and an ECM cell type. The next thing we're going to do is we don't have any chemical fields that we need to think about, so we're going to ignore that field. And the other plugin we're going to add is basically focal point plasticity that's going to help modify each of these properties. Okay. So I'm sure this is pretty basic to you by now. I hope you have done it. I'm just going to wait just a little bit to make sure we're on the same page. So 4 things so far. We have set the X and the Y dimensions of our simulation. We have added 4 cell types, which we're calling apical, lateral, basal, and an ECM. We're going to ignore the chemical field window. And we're going to make sure we have our focal point plasticity plugin clicked. Some of the other plugins that are going to be useful to us are also the cell neighbors. So that should be clicked automatically, but if not, make sure it is. And and contact internal as well. Okay. All right. So the next step, so we should by now have a complete configuration with the plugins all loaded in now. And we're going to now go to our XML file and sort of look at what's happening with our focal point plasticity plugin. So far, the next sort of like modifications that we want to make are in the XML file. So by now you should have an XML file that sort of shows you the uniform initializer site. And the uniform initializer will automatically take each of these cell types. And if you specify the width in the width panel, it will just populate, all of the simulation space that you specify in the box min and the maximum region, and will fill these cells randomly in that area. But what we actually want is sort of like a compartmentalized epithelial layer, which, like I said, we should have ECM at the bottom, basal on the next layer, the lateral on the next layer, and the apical at the top. So that's what we're going to do. We're sort of going to like modify the uniform initializer properties to sort of achieve that layer. Okay. So this is what I mean, because an epithelial cell has a highly polarized body, and when we're representing the basal to apical hierarchy, we are also representing sort of the internal biology of the cell body that shows this polarization. So one way to do this is sort of like know the box min and the box min max levels for our Y coordinate, and sort of set those values and create up a layer of maybe starting from an ECM layer of having a certain Y dimension and then working from that value. So this is what we're going to do in the next step. So what we have done here is we have taken the uniform initializer snippet. And what we have done is we have replaced the X tag from the X minimum tag to 0, the X maximum tag to 350. We have set the Y minimum value to be 0, but we have specified that the Y maximum value is 35. And now if we specify width of 35 in the next tag along with the ECM cell type, and if you actually run the simulation, or basically just step the simulation, you should see an output in which you have a layer of ECM at the bottom. I don't know if everybody has this or is working along with the code, but this is our first step to sort of building the epithelial layer. All right. The next step, what we're going to do now that we have the ECM layer, we're going to add our next cell types. Our next cell type is going to be the basal cell. So what we're going to do is we're going to add an additional region to the uniform initializer snippet. And we're going to just begin off where we stopped with the ECM layer. So now we have expanded our uniform initializer to have a minimum value of 35 at the 35 pixel position, and it goes to the 42nd position, but basically it goes from 35 to 41 because this is a Python syntax. So what's going to happen is if you specify a width value of 7 here, you should now, if you step the simulation, you should be able to see your ECM plus basal layer in the simulation. And we can keep going this way what we can do is we can sort of modify our next values to have both the lateral and the apical side, so that now we have a complete set of apical, lateral, basal, and ECM cells in the simulation. Now, is everybody on board so far? You have seen this before. Is this a simulation you're comfortable with? Let me know in the chat if there are any issues so far, but I'll move on ahead. Okay, so our next step sort of is going to be making sure we have the correct target volume set. The volume plugin that you loaded in should have the corresponding target volumes and the lambda volumes of the other cell types. But for the ECM, make sure that we have 35 times 35 as the target volume correctly set. So now, if you run the simulation, so what you have in the simulation so far are not a lot of plugins. You have the volume, you have the contact energies that we haven't messed with, and you have the focal point plasticity plugin. So if you do not change anything in the focal point plasticity plugin, and you just run the simulation, you should be able to see an output where you have these white lines between every cell type, depending on your maximum maximum junctions allowed and the nearest neighbor order parameters that you have chosen. You should be able to see them popping up in the simulation. Does everyone have this and are able to build this simulation layer with the links? Could you let me know in the chat? Okay, perfect. Thank you. So now what we're going to do is sort of two things. So when I described the problem, I told you that we need to sort of generate particular stresses in certain regions and along the apical body. So right now, the simulation that we have, even though we have sort of built these different compartmentalized cells, they are, first of all, not connected to each other. So they don't have a cell body that could deform under the weight of these stresses that we can add to them. And secondly, we have links that are connected to every possible cell type because we haven't modified any of the focal plugin parameters. So that does not selectively give us the opportunity to induce stresses only at the level of particular cells. So right now, our simulation needs to be modified on those two grounds. We need to make sure we have a cohesive cell body, and we also need to make sure that our parameters are on the focal point plasticity side are only applied at specific locations so that we could exert forces on them. And so these are the two steps we'd be taking care of. Let's work with, let's sort of like just remind ourselves what the ultimate, like the focal point plasticity plugin does. So our focal point plasticity is going to be comprised of 5 different tags. So Julio has already told you about the lambda parameter that sort of dictates how strongly the link between those two center of masses is going to be applied to. So if you have a higher lambda, you basically are pulling on the two cells more strongly. You have this parameter of activation energy that sort of is added to the internal energy function and sort of makes it more favorable for a link to be created in that simulation. We also have the other 3 parameters of target distance. The target distance is what you want the distance between the two center of masses to achieve. The max distance is a parameter that you can set to sort of cut off the link if the distance between the two cells become higher from that point. The maximum number of junctions sort of specify how many junctions or how many cells each you want each cell to be connected to. And I think Julia has already told you about this neighbor order, which is a local tag of neighbor order that you can modify inside each of the apical inside each of the particular focal point plasticity parameters. And the other, there's also a global neighbor order that you can adjust so that you could, if you want your parameters to be, if you don't need to modify your parameters more locally. Once we know what the focal point plasticity features are, before going into the steppables file, we also need to make sure the contact energies are modified. Oh, sorry. Let me first actually walk you through the focal point plasticity parameters first. Okay. So if we want to modify the focal point plasticity parameters, we have to uncomment this local tag. This allows us to modify any of the plugin parameters from inside the Python simulation. And like I was describing in the problem that we only need specific connections between the apical to apical side, we're going to remove all other tags between any other different kind of compartments. So anything except for the apical tags, we're going to remove from the plugin. And so you can just delete the rest. And we're also going to do the same thing for the internal links, because the simulation automatically would have created internal links that once it realizes that the cell is part of clusterized compartmentalized cell, it would have also put internal links between members of a cell. So we're going to remove everything so that your focal point plasticity plugin region only looks like this. So you should only have the apical tag. Right now, there are some parameters in, and we'll go over that in a second. And we should have the local tag activated. But apart from that, everything else should be gone by now. And if you now step the simulation, you should be able to see that you have an epithelial layer comprising of all of these, and you should be able to see links on the apical side, but you might be able to see only some links. And the reason here is, in this particular snippet, I have set the maximum number of junctions to 1. So their cells are just forming links between their neighbors, but they don't have enough to go around and form links on both sides. So randomly getting links on between some number of neighbors and not everyone. Okay. I hope this makes sense so far. This is where we have sort of modified the focal point plasticity plugin to only have links between our apical and apical side. Okay. The next thing we're going to do is we're going to modify the focal point plasticity's properties from the steppable file. So one thing we're going to do is we're going to set some of these parameters to 0. The activation energy, we can keep it here. We won't mess around with it, but I saw that in CompuCell 4.4.1, at least, you also have the opportunity to change the activation energy from inside the steppable function. So that's something too, if you want to change from inside Python. But the rest, all the lambda distance, the target distance, the maximum distance, the maximum number of junctions, we're all going to set to 0 at this point. So there is a question in the chat. Let me read it up. The question is, why are there no links between basal and lateral? You can absolutely form links between them. And a fun exercise might actually be trying to change the target distance between their links, their compartments, to try to see how the shape of the tissue changes. Along with changing properties on the apical side. Here, for the problem that we're only inducing certain specific forces on the apical side, we're not doing that, but you can absolutely do that, do that exercise. All right. So if now you actually set up all of your parameters to 0 in this code snippet, and you actually step through the simulation, you should be able to see that the links have all disappeared because you have set the lambda properties of this to be 0. Okay. So now we have actually 2 more steps to go through before we get to the actual steppables file. And Julia has already talked about this problem, because when we have compartmentalized cells, we want the different cell types to stay together, but also sort of like lay side by side to demarcate the basically structure of the epithelial tissue in general. And so the rule that Julie has already described before is that we want the cell types that represent a cell body, basically the apical, lateral, and basal, to have sort of affinity to each other so that they stay together. And so the values that we have chosen for this is basically just setting the values to 2, and everything, the rest of the values, you can set it to 0. More specifically, because you obviously don't have 2 apical compartments on each side, so the contact internal energy for that is not applicable. In some other cases, for example, you do not actually have contact, and the ECM is not compartmentalized, so you don't need to worry about internal contact energies between them, and so on. So the only 3 contact energies you need to worry about are apical lateral, apical basal, and your lateral to basal. And those are set low enough so that your cells will stay cohesive together. Okay. The other thing that we have to do is sort of like now set up the external contact energies. And the external contact energies, again, we have to be careful that they should be set sort of like low enough for the different compartments of the same type to lie next to each other, but they shouldn't be set lower than the internal contact energies. So the rule, again, that we followed was sort of trying to set that the apical to apical, the lateral to lateral, and the basal to basal values are set low enough, but not absolutely low. So we have set them to a value of 5. You want the apical side to sort of like face the medium, which is basically, you can think of it as the outside of the cell. So that value also is set low so that the apical side can be like pointing outside and in contact with the medium. So that value is also set low. We want the basal side to sort of represent the fact that there are molecules like integrins on the side that are going to actually interact with the extracellular matrix protein. So you want the basal side to be more very adhesive to the ECM. And so that energy is also set low. The other thing is some of these compartments, like the apical to ECM, you definitely don't want that because they represent like different surfaces of the cell body. So those energies of apical to, say, ECM, to basal to the medium, those have to be set very high. But in between, the energies of sort of the apical to lateral side, that can be set to a sort of like highish value of 10. But the extreme opposites, those should be set to very high so that you have no chance of the cell wanting to sort of like come over and talk to the ECM in any case, right? So the values we have chosen for the lowish values are 5. The highish values are 10, and the very high values are set at 20. Okay. All right. So now if you run the simulation, you should be able to see sort of a little bit more cohesive structure in which the compartments would like to sort of either face a particular side or stay next to each other. We still have a problem here because we haven't sort of initialized the cells to know that they're part of the same cell. So we haven't solved that problem yet, but at least now we have set the contact energies so that compartments of the same kind sort of like each other and so on. All right, I hope this makes sense. Okay, so now we're going to actually go over to the steppable side of things. And what our goal here is that we want to sort of do two things. We want to reinitialize all our compartments to feel like they're part of the same cell body. And this is what we have used in Julio's code this morning as well, to sort of use the reassign cluster ID function. And the other thing we're going to do is we're going to manipulate the focal point plugin parameters so that now we can bring back our links and do some stuff with them. Okay, so if you're following along with the code, let's first go to the start function, where we'll be writing or modifying some code to connect all of our cell compartments. So this is the snippet that you had used this morning, and the sort of like the code idea, and you can come up with your own way to sort of know that the cell that you picked is sort of another it should be part of the bigger cell cluster. So the code that Julio had used was he looped through one cell kind. In this case, it was the apical kind. And then he picked out the center of mass of the apical cell. And if he was able to identify a lateral cell which had the same center of mass in the x dimension, meaning that they were placed exactly on top of each other, only displaced in y, but not along x. That would mean that they were part of the same cell. And he used a function called reassign cluster ID to sort of assign this newfound, to assign these cells ID to the original apical cells cluster ID. So he can do the same thing for the basal side. And this should have the advantage that now he's able to connect the all these cell center of all these cell types that he thinks should comprise the bigger cell cluster. So I don't know if people want to copy this. You can either copy this from the original code this morning. You can also copy this from module 6.4 where these lines should be there, or if you want to type it out, that's fine too. I'm going to just pause for a moment here. Please let me know if there are any questions, and if this makes sense. Are people able to follow along? Or have you gone through this step, and should we move on? Okay, perfect. Thank you. All right. So now that we have sort of like reassigned our cluster IDs, what we're going to do is we have to now modify our focal point plasticity. And I think there was a question a while ago on how do you sort of like make links. And in this case, we're indeed going to actually visit cell neighbors. And we're going to, basically the flow, what we're going to do is use the cell neighbor tracker to find apical cells which are next to each other, or basically which are touching each other. If they are, we're going to form a link between them. And, we should be able to, because of the way that we had set up our initial configuration, we should be able to reach all these cells in the tissue layer. Okay, so again, where do you find where cell neighbors is? You probably know this by now, but if you go to CC3D Python, and if you go to visit, you should be able to see cell neighbors, and you should be able to, pulling out cell neighbors should give you the snippet of for neighbor and common surface area in get cell neighbor data list. And we should be able to get all of the neighbors that a particular cell here has. For the top case, what I have done is I've looped over all the apical cells first and then found the neighbor. Also notice that there's a tag that says if neighbor. This is just to exclude any medium cells. The other check we're going to make is if neighbor type is self-apical, because again, we want to form links only between apical sites. So that's why we're double checking to make sure that the neighbor that identified is an apical cell type as well. Okay. If you want, again, copy the code or write it down. Again, this is also in module 6_4_1. All right. So now, after we have done this part where we have identified the other apical neighbors for a particular cell, we're going to set up links between them. And for that, we are going to use the focal point plasticity, which is again accessible through the CC3D Python window. So CC3D Python focal point plasticity, go to link management, and then create an FPP link. And if you do that, this should pull up these couple of comments. And I think this line will probably be commented as well, which you can uncomment for our next step. So basically, this creates a new FPP link between the cell, between each apical cell, then the neighbor that we had identified using our cell neighbors. And then we have room to sort of decide our lambda parameters, our target distance parameters, and our maximum distance parameters that we want. So in this case, the lambda distance that I have set is 10. The target distance, I have set it to the width of each of these compartmentalized cells, which is 7. The maximum length, I've set it to 200. In this case, I don't really care. But if you have simulations in which you need the links to break after a certain point, you can certainly change that accordingly. Okay. If you have implemented all of these steps, for example, reassigning the cluster IDs correctly, visiting the cell neighbors, and then setting up the FPP link, you should have a simulation in which you should see all of the apical compartments connected with this FPP link. So I'm going to pause here and make sure everyone has this. This should be the output from 6_4_1. If you run this, this is what you should see at the end. I'm going to quickly monitor the chat. Okay, great. Thank you. Going to wait a few more seconds. Okay, so all right. So if you have the simulation where you have set apical links all between your apical links connecting every cell, now we come to our main problem of how do we sort of induce this fold. And right now, the current problem that we have is that we have symmetrical FPP parameters connecting every cell of the tissue layer. But for example, if you see a problem like invagination, the fact that there are certain cells which have a different shape than the rest of the tissue sort of indicates that there has to be some differences in properties along the tissue body. And so let me actually ask you the question now. So suppose I need to now sort of bend or fold the tissue, what would be the best use, or what would be a way to sort of adjust my focal plasticity parameters to do that? So I don't know if you have any suggestions or answers on that. What would be the way to sort of like fold the tissue, and what would be one way to sort of like achieve this invagination using the focal point plasticity plugin? Okay. So I don't see any answers yet. Okay. So the way that we are going to sort of do this is by selecting a group of cells that effectively lie in the middle of the tissue. And we're going to change their focal plasticity parameters specifically. And we're going to, in this case, we're going to change their lambda distance, and we're going to change the target distance. And we're sort of going to change those properties only for the specific group of cells, and see what that leads us. So here is the part of the code. The actual module for this is 6.4_2. So if rather than typing it in, you would like to copy the part of the code, feel free to do so from this. But if you're following along, what we're going to do is we're going to now go to the step function. And the reason is we want some more freedom in sort of identifying a particular time point in which we are able to manipulate these properties. And I mean, even in like sort of development, we want the time point at which, you see a morphogenetic event could be variable. So we want to sort of like specify a time point after which you want the invagination process to start. And for that, we're going to use the step function here, which has the argument of the MCS steps that we're going to use. And we're going to also go back to our focal point plasticity plugin. And we're going to do two things. First, we're going to specify that this is a time point after which a particular event could begin. In this case, we have specified the time period of 500 Monte Carlo steps. So we're saying that if MCS is 500, that's when you start sort of invaginating. We're also going to pick a particular region because that's how we're going to implement this asymmetry in the focal point plasticity parameters. And so what we're going to do is we're going to go to our cell type of all the apical cells. We're going to pick a particular region between 125 pixels and 225. And we're going to only pick cells that lie within that region to sort of implement our focal point plasticity parameters too. And to actually implement these steps, we are going to go to CC3D Python, focal point plasticity. We're going to go to visit all links attached to a cell. And those are the specific functions that we're going to change there. Okay. So if you go to visit all links attached to a cell, it should pull up this code of for link in self get FPP links by cell. And that's the link property that we're going to modify. Hope this makes sense. So yeah, basically we're picking up a particular time point to implement the force changes in, and then we are picking up cells between a certain region, and then we're visiting all of our FPP links in that region. Okay, so the next thing we're going to do is we're going to, again, go to CC3D Python. Like once we have gotten a link that connects to cells, we are going to modify the link properties. And the same tool, the same plugin window also allows us to manipulate sort of the internal focal point plasticity parameters. So CC3D Python, focal point plasticity, link parameter. If you click on link parameter of lambda, it will allow you the option to rechange the lambda distance. And if you now also do the same process, go to CC3D Python, focal point plasticity, link property of target distance, you should be able to set the target distance to 3. So what you have done here, just to recap, is visited all of your apical cells, gotten the link identifier for each of these cells, and we have tried to modify that specific link properties by resetting the lambda distance and by resetting the target distance. And we have done it only between a specific region of 125 and 225 pixels along the x-axis. So now, if you run this simulation, this is what you should sort of get. So if you wait for some time, you should be able to see the sort of like tissue fold emerging, which is between that particular region that you had picked out. And this should, what you should see is that the apical cells in that region have sort of like coalesced, that they're trying to come together because we have sort of reduced their target distance from the typical width that they had to something like 3, and they have to like maintain it. So as that link, the FPP link, is shrinking, the cell centers of masses are pulled together, and you see the apical side clustering, but the basal side is so far unaffected in this case. So you sort of see a fold appearing along this. Does that make sense? Let me know if there are any questions. I'm going to pause here for a minute to see that everybody has gotten the same simulation or is able to reproduce this output. So I'm trying to reframe the question asked in the chat. So we're not actually acting in the link positions, always in the CM, right? So the links are actually connections between the center of masses, and sort of the focal point plasticity is sort of like pulling on the center of masses to bring them together. Is this the slide you were referring to? So this is the slide where what we had done was we had looped over all the apical cells. We had picked out certain cells between 125 and 225 pixels. And then what we're trying to do is sort of get the link attributes that connect these different cells. And we're trying to modify the link properties by resetting the lambda distance and the target distance. And what this is achieving is by modifying the link properties only between these specific groups of cells, we are able to sort of bring certain apical compartments closer to each other and not moving the rest of the tissue, so that we get sort of a fold or invagination appearing. All right, so I'll just wait here for 30 more seconds, and then we can all right. So now that we have this, we should get this output where we see this invagination. Do people have this, or are we still working on it? So while you're working on it, there may be a couple of things that you could try. One thing could be that we set our lambda distance to a particular value and our target distance. Maybe you can try changing the lambda distance to a slightly lower value of 30, and you can check what happens. And the other question is, we had this particular line in the code that allowed us to pick cells in a certain vicinity between 125 and 225. Suppose that did not exist. How would the output change in that case? And maybe you could try that as well. I'll stay here for a minute more to see if there are any questions. But just to summarize, so this is the basic concept behind like generating specific forces in CompuCell. Here we had used the focal point plasticity plugin to sort of like create an asymmetry in a specific region. And we had changed the FPP properties to pull certain compartments together. And you can sort of use the same sort of ideas to change other cell shapes as well. For example, if any of the internal focal point links were still kept, you could additionally change the lambda properties to sort of elongate the cell body. You can try putting basal links in here as well, which might not be biologically relevant, but you could check what happens if you additionally put links on the basal side, and how along with changing properties on the apical side, what the shape of the tissue looks like. You're also, if you want to elongate a cell body, you can put links between the basal and the apical side, and additional links between the basal, lateral, and lateral apical side to sort of elongate the cell body. So the focal point plasticity enables you to sort of like separate these cell compartments and like change cell shape values. Okay. Did anybody try the changing lambda? So Sharon's code broke on the right of the contracting edge. Let me see the image in greater detail. I can't. Oh, interesting. It seemed that the lateral cell, so one of the lateral cells sort of went in, and the apical cell started making contact with the basal side. I am surprised that this would happen without changing any of the properties, unless either the adhesion parameters are changed or something else. One possibility is to make sure that the cells are still have been reassigned and are part of the compartmental cells, and that they're not behaving independently of the internal contact energies. So that would be one place to check, but that's interesting. Is anybody else facing any issues? So you can try running the 6.4 Interesting. So this is with lambda of 100. Right. So now what seems to happen is if you're forcing, so I can't see the other two compartments here, but what is happening is if you have increased the lambda distance to very high of 100, the compartments like are really forced to sort of maintain their target distance. And so they at this point, they do not care about all the contact internal energies that you have put in. And so the cell sort of is like fragmenting, but they're really forced to sort of maintain the target distance. So yeah, if you keep increasing it high or set the target distance to even lower, you might end up with fragmented cells like this. I don't know if there are any guesses of what happens if you increased the lambda distance uniformly for each of these cells? Right. So one of the answers is a big bend. So I would actually try that. It might not be the answer you expect, because now, yeah, so Sharon has an answer on, for uniformly, I guess that a tissue wouldn't bend at all because of the periodic boundary condition. It won't be able to. And that's correct, because now if you have sort of uniform forces without actually specifying these certain specific regions of high force, even if you increase the lambda distance, because you're doing it uniformly across each of the lengths, they would all experience sort of the same force increase, and you would not see this bend. So sort of this asymmetry is like crucial to constructing this invagination. Okay, so I think we have about like 15 more minutes. So what we can do now is we're going to talk about 2 more modules. They're a little more Python heavy, but it's a fun exercise where I'm just going to give you the key points of the code, and you can run it and tell me what you found out or thought of it. So far, what we have done is we have picked up a particular region and sort of invaginated inwards around that region. But we can also think about applying this to a more biological context, which is that of formation of somatogenesis. This somatogenesis is this process of periodically delineating groups of epithelial tissue from the presomatic mesoderm. And it's a very periodic process, happens sequentially and periodically in time and space. What we want to sort of like, what we also see in somatogenesis is that the cells that make up a somite are highly epithelial in nature, but they are not always epithelial. Over time, they undergo a mesenchymal to epithelial transition, become epithelial. And as they're able to sort of break down into these balls of somites, they sort of have these rounded surfaces, and these rounded surfaces demarcate the boundaries of consecutive somites. So we're going to do a simple exercise from a CompuCell point of view, but the goal was sort of to mimic the rounding off of consecutive epithelial-like balls along the anterior posterior axes. And what the kind of questions that we're going to be exploring is, how do we get uniform sizes of these groups that will break off, and if using the focal point plasticity parameters, we're able to like sort of reproduce number one, a sequential from the anterior to posterior breakdown into these different like balls, epithelial like balls of somites. And the second question is, how many cells can we fit in each of the balls? So for example, in the simulation below, what I'd classify as, if you can see my cursor, what I'd classify as one unit would be this group, another unit would be this group. And I can see that there are 1, 2, 3, 4, 5, 6 cells that make up this group. So using the FPP properties, can we start with a uniform tissue layer, sort of break it down sequentially from the anterior to the posterior, and at the end, calculate how many cells we have in each group that sort of also are rounded off, as we can see in the somite formation process. So to do this, feel free to download module 6.4_3, I believe. So we're going to be doing it in 2 parts. And the 2 parts are basically, we're going to try to sequentially activate our cells to change their focal plasticity parameters. And the second thing we're going to do is, once their focal point plasticity parameters have been modified, we're going to use it to make an epithelial ball. Okay, so the couple of steps that we're going to do this is, now that we need to change the FPP properties sequentially from the left to the right, we need to sort of understand some positional information of where we begin with the FPP properties and where we end up in being. And so to implement this, what we're going to use so what we're going to sort of try is to go over from sequentially from the left to the right, and we're going to change certain attributes that allow us to modify the focal point plasticity from the left to the right. So if you look at the code snippet, if you want to look at module 6_4_3, the code snippet is actually in line number 74 to line number 96. So these are the things that additionally I have added to the code. I'm just going to walk you through it. Don't, if you don't want to copy any of the text, you don't have to. So what we're trying to do is, we're going to go from the left to the right. We're going to identify a parameter called wave speed that allows us to identify at which point the next cell is going to be responsive to the change in the focal point plasticity parameter. And we're going to only change the focal point plasticity parameter in those cells. So what this is going to achieve is that instead of seeing a group of cells constrict all at once, you're going to see a wave of focal point plasticity activity in which cells in the left are going to change their properties first, and it's going to propagate all the way from the left to the right. So this is the part where we are using this parameter of wave speed to sort of go over our list of all the apical cell IDs. And we're going to identify if a particular time has passed to update a counter called constrict so that it is now ready to change that focal point plasticity. And the actual modification is sort of made in the next part of the code, where we are checking that if it has passed that parameter of wave speed and has now set the constriction parameter to 1, it's now ready to start constricting. The other interesting thing, like I said, that you can also change these focal point plasticity to elongate and change properties over time. What you can also do here is you can get the same sort of information on the target distance or the lambda distance that you had gotten before. And then you can change the parameter slowly so that the length modifier between the two cells are gradually changed instead of being changed all at once. And the other function we're going to use is the set lambda distance function. So we're going to sort of like have a time, identify that after this time, this cell is sort of responsive to the focal point plasticity plugin, slowly change the lambda distance in this case, and then see the effect. And this is a rate that I have associated with this with the simulation. You can basically change this parameter to sort of see how fast or slow you can modify any of these parameters. And I've set a maximum lambda distance of 100. That's the limit after which I know my cells will be prone to fragmentation. So this is a value that I have set it to. Okay. So now if you just run the simulation, you should be able to see just a wave of cells responding to the focal point plasticity plugin, and that they're like all getting huddled up together. But what I told you before is we also want to sort of like fragment this tissue into different groups and sort of identify how many cells are present in each of these groups. So what we're going to also do is sort of measure how much the focal point plasticity parameter has changed between each of these cells and identify how stressed or how tense the link between those cells are. And what I mean by that is the following. So if you see this particular simulation, what you're going to see is that these cells, some of these cells have more freedom to sort of come closer than the others. The cells in the middle, they don't have a lot of room to move, because as more and more cells get added to the right of them, they are sort of like stuck in these positions. We have told them that they need to maintain the target configuration, but they're not able to do so. So those cells are very stressed in the middle. And we are going to exploit that property to sort of identify how tensed those links are. If they become very tensed, we can break at those particular positions, and sort of that will become our unit or our group of cells that will form a group, that will form a chunk of tissue. So let's go do that in the next module code. So 6_4_3 should give you the sort of like setting up the wave of sequentiality from the interior to the posterior. This is the part where we're sort of trying to segment the tissue. And what we're trying to do here is, for each of these cells that we have identified our links in, we're going to get the measure of the tension of that link. And this formula basically comes from defining the energy function. It's basically proportional to the lambda distance that each of these cell links have, and the distance that they're able to maintain. So if you sort of have a high lambda, you're basically getting more stressed, but you can sort of like remedy that by sort of being able to reach your target distance. So if this value is sort of small and you're able to reach your target distance, then your tension might not be as high. So the combination of these two factors is what makes a cell, that link, more tensed or not. So what we're going to do is we're going to calculate this parameter, and then we're going to collect all these cells that have crossed a certain barrier. And if they have crossed a certain barrier, we're just going to break those particular links. And if you do that now, what you should be seeing in the simulation, or basically if you run module 6_4_4, is you have a wave of focal point plasticity changes along the interior to the posterior direction. Some cells are going to respond to this change in the focal point plasticity better than the others. Mostly cells who get stuck in the middle, they will be the ones to break. And in the end, you're going to get sort of these clusters that form, and that sort of demarcates a group of cells. So this is what it looks like over time. I'm going to quickly check the chat if you're still with me on this. If you run module 6_4_4, there should what the output looks like. So I know that there were two concepts in there which were more Python involved. So we sort of defined what we meant by tension, which is a formula that came from the energy function. But in like a nutshell, it's basically proportional to how closely we are able to reach or attain the target distance that we had set, multiplied by the lambda distance of the simulation. And if a cell is not able to basically reach the target distance at all, and it has a very high lambda, it's very susceptible to basically be picked out on our breaking list. And once we have identified the link, we can sort of even using Python sort of break that link and create these clusters of cells. Okay. All right. So the final question that you can sort of ask here is the following. So now we can use our parameters in the code to sort of break the tissue. What do the sizes of all of these groups look like? How are they uniform? There are two parameters which are really very interesting. One is that wave speed at which you are sort of inserting new cells to be added. So if you have a very fast speed at which you are sort of like incorporating almost every cell in your simulation, something very interesting happens, that the cells don't like fragment into smaller groups anymore, but they're very large groups that they will break into. Consequently, if you have a very fast speed, then cells are going to be activated very fast, and you should check out what the output in that looks like. So in module, let me check out the line number where these, you can modify the wave speed. I believe the, one second. So the speed at which the focal point plasticity properties are changed, that's on line number 75. That's the wave speed parameter. Feel free to change it and see how it changes. The other parameter you can change is in line number 100. That's the breaking tension value. So you can also reduce that or increase that and check out the number of like clusters that form here. And the other thing is that you can plot a bunch of stuff if you want to get practice with visualizations. So this is an example where I had just plotted the number of cells in each group, but you can also plot sort of the average size of these clusters as they break. You can sort of you can also sort of like mark the what else can we do? Yeah, you can sort of change the length of the entire simulation, and then try to see how the sizes of these groups change for a smaller simulation versus a larger simulation. The first couple of groups that break next to the boundary condition will always be a little bit weird, but then you should start seeing this uniformity, and you should see how it changes for the simulation size and convince yourself that that works. Yeah, play around with the wave speed value, the tension threshold value, and the breaking, and also the lambda change value, which is basically how fast you're sort of like increasing that lambda distance. Okay, so this sort of concludes what I had for you today. I'm just going to pause for a moment and sort of see if people did play around with both of these simulations and if they have any output to share or if there are any questions.
Good question from Julio in the chat, saying not just for Priyom, but again, how could we explain in an article that using this approach would be the way it works? So I think what you're asking, Julio, is how would you explain in an article that this is accurate to the real world?
Well, Priyom may have an answer for that, but fundamentally you're applying forces, and this is a way of applying linear elastic forces. And so we know that, for example, the cytoskeleton in the cell applies forces, sometimes linear elastic, sometimes constant force. You can select either of those options. Ultimately, what we want to do is have a phenomenological replication of force generation, and I think this is a situation of that kind. Remember that nothing that we do here is first principles. It's always phenomenology. And so provided that the constitutive relation, the force-velocity relation, is replicated correctly, we can't ask what is happening at the micro level. For example, with chemotaxis, it's not that the chemical field applies the force to the cell. the cell responds as if the chemical field is applying a force to it, but in fact, the cell has chemical receptors on its surface that adjust the cell cytoskeleton so that it moves actively in a given direction. And so a lot of what we do is to try to replicate the behaviors that are observed, but not worry too much about the microscopic behavior. Again, think of a car driving. When we say that the car accelerates, we're not modeling all of the components of the engine.
I think James already gave a great answer, but what I could add is what you're searching for is to like replicate a phenomenology. And if that framework is sort of useful, or representation by center to center forces in this case is useful, you're able to replicate and sort of predict outcomes that this can represent, then it would be a good system to use. And this is not the only way to represent, forces. There could be multiple ways, but as long as it fits within the scope of your problem, as long as it's able to generalize the biology that you're looking to capture, it could be a good fit.
Julia makes a good point. But what's the difference between an animation and a simulation? And this is a subtle question. If you look at the physics engines that are used today in generating animations for CGI movies or video games or anime, they're extremely sophisticated. They don't always have exactly the same physics as the real world. They sometimes take some shortcuts, but they actually have an enormous amount of physics in them. And so a lot of animations actually have a great deal of physics in them. And I've often been tempted to say maybe we should be going to NVIDIA and using some of their animation engines as the core for building simulations, starting with something like Blender and using the back end of some of NVIDIA's very high performance parallel processing for video graphics. But one of the things that you could think about it with phenomenology is, suppose that I started out with a simulation. It really was an animation. I put in everything by hand. Or as I just say, move this cell here, move this cell here at this time, move this cell here at this time. If I can then go backwards and little by little put in mechanism and replace the things that are imposed on the system by biologically or physically plausible mechanisms, I move the boundary between animation and simulation towards simulation, and the explanatory power of the model goes up each time I do that. The issue really isn't, is it an animation or a simulation? The question is, how much scientific hypothesis is embodied in the model? And ultimately, we have to decide where we draw that line. We can't model everything, and so we have to make a choice about that. And different people will have different legitimate ways of making that decision.
That's actually something that we can investigate a little bit tomorrow too, during our hackathon brainstorming session. Thinking about a project of your own and how to scope it down into a feasible CompuCell model is actually a good way to make some of these more abstract, abstract modeling abstractions a little bit more concrete.
Sharon, those are great points. Maybe unmute and ask out loud, because it would be good to have those in the record.
Sorry, I make the same mistake every single time. I guess I'm not really asking anything, but if you want to comment on what I said. I mean, the first one there, I might have written it too succinctly, but by saying it's a spectrum, I guess I mean you were talking about backing out from animation down to simulation. and I mean, it's a spectrum sort of from top to bottom. How far back you have to go depends on where your question is, it seems like. And the other one, L systems, I never got very deeply into it because I didn't like them. But I read a little bit about it, and yeah, they made amazingly impressive movies of things growing and branching and whole forests. But it didn't feel like the math had anything whatsoever to do with physics or biology. It was just pretty. You're muted.
If you can make a convincing animation of something, you've actually had to understand it quite well. And even if there's not a lot of mechanism in the animation can be useful in helping people understand how a system works. And so I think that we shouldn't dismiss the idea of making effective animations. That can be a very useful thing to do, and it can aid scientific understanding. And we can learn. As I mentioned before, just trying to decide what we need to know to build a model that works. It's executable. We may find gaps in our understanding, or we may identify logical inconsistencies in what is commonly understood about a process. And so I think that the discipline of building models or the discipline of building animations both can teach us a great deal about the complexity of biological organization and function.